Greetings. I am Cary Chun, the lead author for our project, a terrestrial mission extension module for Radiosonde weather balloons. My research team also included Andrew Smith, Joseph McBride, Kaveh Torabzadeh, and Santana Roberts. Radiosondes are balloon-assisted meteorological instruments that are commonly utilized in the continental United States. And while hundreds of these instruments are launched every day, only a small percentage of these devices are recovered and reconditioned for reuse. This design team was therefore interested in developing a system that could be attached to the bottom of an existing radiosonde to protect the device during its parachute-assisted landing. Such a landing system could also provide supplemental power after the radiosonde had landed, converting the high-altitude meteorological instrument into a surface-level monitoring station. To make this research project feasible, only the mechanical landing system was explored. However, the potential impact of a fully functional radiosonde mission extension system could be numerous. Such a system would allow an area without the means to afford both ground-based and high-altitude meteorological monitoring systems to achieve both by simply launching inexpensive radiosondes. Furthermore, by maintaining a telemetry downlink from the radiosonde after landing, the recovery rate of the devices could be drastically improved, which would decrease pollution and encourage sustainability. In developing the mechanical landing system for the Radiosonde mission extension system, a number of archetypical designs were considered. The designs were then rated by the design team in regards to a number of required design criterion for the final system. Through this process, it was decided that some form of deployable mechanical spring-assisted landing leg would be the best option for this project. With some rough hand sketches of the system completed, a common computer-aided design software was utilized to create a virtual model of the assembly. The final version of this model featured an adapter bracket for connecting the system to the radiosonde, vertically stacked over an electronics enclosure that was nestled within an aeroshell, situated just above the landing legs. To view the internal mechanisms for deploying the landing legs, a cross-sectional view of the model was produced. In this figure, the system is viewed in the deployed state, with the sliding rings that carry the connecting struts locked in its deployed position. Comparing section views of the model with the landing legs in the folded position, as with the bottom two images, and in the deployed state, as with the top two images, the significant change in the width of the landing stance is clear. Before fabricating a real-world prototype, some additional mechanical analysis was completed on the CAD model. First, the degree of freedoms of the deployed landing legs system was compared to the same system in the deployed state. Since the system in the deploying state maintained 5 links, with 4 full joints and 1 half joint, the system would be expected to have 3 degrees of freedom. These 3 degrees of freedom allow the landing legs to move down and outward while the landing feet rotate. By comparison, the same system in the deployed state would have only 4 links and 4 full joints, leaving the system with only 1 degree of freedom. To further explore how this single degree of freedom would be manifested in the mechanical system, an additional analysis was completed. If treated as a 4-bar mechanical system, the deployed leg struts could be considered as a Grashof mechanism. More specifically, with the ground link opposite to the shortest link, the system would act as a double rocker, allowing the landing foot to move along the red arcs in the figure. This was a desired outcome, as the landing foot would be then capable of adjusting to an uneven landing terrain. In anticipation for field testing of the prototype system, a number of digital simulations were also completed. With a static load applied to the modified version of the landing system, the lowest factor of safety and highest stress was observed at the shock absorbers. Since a minimum factor of safety of 1 was not obtained in the static loading tests, there was the expectation that the shock absorbers would be the most likely component to fail in the real-world test. Digital drop test simulations were also completed, with these results further suggesting that the shock absorbers would be the most likely weak point in the system. To create a real-world model of the CAD assembly, the custom-modeled parts were 3D printed utilizing a fused deposition manufacturing printer. All parts were created utilizing polyionic acid filament. In the first phase of prototype experimentation, a modified version of the landing assembly was crushed in an MTS machine. Initial results from these tests showed good correlation with the simulated static loading, as the shock absorbers were the first elements to fail. Additional analysis revealed the landing system maintained almost 700 newtons of applied force before any failures were observed. Since the landing system was expected to be assisted by a standard radiosonde parachute during landing, the second phase of field tests focused on developing a methodology for determining the landing velocity of the parachute payload. Numerous integrated data loggers were tested with an arrangement of sensors. However, while benchtop testing implied that these systems could be used to determine the relative velocity of the payload, field tests proved to be far more dynamic, and the simple data logging packages were ultimately deemed inadequate. Using a calibrated payload and parachutes, another technique was developed and validated. By placing a length scale within the view of a video camera, the time taken by the payload to pass the scale could be ascertained. The average velocity could then be computed for the payload. With a means for determining the landing velocity, a location for completing the drop tests, as well as consistent method for conducting these tests was required. A number of potential testing locations were investigated, but issues with the parachute payloads becoming snagged on walls and inconsistent payload releases abounded. To combat these problems, a simple 3D printed quick-release system was developed. This quick-release system was then attached to the end of a collapsible PVC boom. In tests from windows of buildings, the quick-release boom could ensure the payload was released away from the side of the building, while tests performed from man lifts allowed the boom to be secured to the lift to ensure the safety of the lift operator. In the final phase of experimental testing, a series of dynamic landings could be completed. By modifying payload mass and parachute size, a number of different landing scenarios could be simulated. These scenarios include a worst-case landing that was at a high speed onto a hard surface, as well as a best-case landing at a low speed onto a soft surface. For comparison, additional tests were also completed with a payload weighted to represent the most likely mass of a finished landing system. Results of these tests correlated well with the previous virtual simulations and real-world crash tests. The custom shock absorbers consistently were the first components to fail. Further observations between all DREP tests also implied that with the added mass of the Radiosonde, the landing system was not exceptionally stable during landing. Therefore, future iterations of this project may need to see significant redesigns to the landing system, including the widening of the landing stance and implementation of stronger shock absorbers. Additional avenues for future exploration include the further implementation of onboard electronics for the landing system. This could include both integrated electromechanical elements for deploying the landing legs and providing supplemental power to the Radiosonde, as featured in the left figure, as well as onboard miniature cameras to be used to observe various moments in the landing sequence. We would like to extend our gratitude to JMX High Voltage for graciously providing facilities and equipment for completing drop tests, and to Vaisala for providing information and sample Radiosonde products. Additionally, we are very appreciative of Kennesaw State University for allowing us to complete this research project. Thank you.